Okay, so let's go ahead and talk about problem number 31 here. This is 6.4, number 31. And this is actually a pretty interesting problem involving physics. Kinetic energy of an object of mass m moving with velocity v is defined to be 1/2 mv squared. That's actually a very important formula in physics. And then when you apply a force, so maybe I should start by saying kinetic energy is just basically how much energy does that object have when it's moving. You, when you're walking, have energy. It is part of your speed, actually, and your mass, and that's where this formula comes from. And kind of an interesting side note about that is if you want to know, let's say, the kinetic energy of a bullet versus the kinetic energy of you, we'll make some assumptions here. First, let me quickly look up the mass of a bullet. Okay, so let's assume that the mass of the bullet is 0.0042 kilograms. And the velocity that we're going to fire this bullet off at is 965 meters per second. And then we'll take half of that result and then we'll square the velocity. And when you do something like this, you'll get how much energy is stored in that object when you fire it out of a rifle or gun. Now, quickly just grabbing a calculator and computing this, I get roughly 19.56. Now, remember, the units are going to be kilograms, meters squared per second squared. Well, so this is kind of an interesting unit. If I write this instead as kilograms, meters per second squared, you'll see this is an acceleration. And this is a mass. Okay. And then I know I wrote two m's there. Sorry about that. I will go ahead and say mass. And then that meters right there is, well, a distance. Right. So let's see, we have mass times acceleration, which is a force, times a distance. Mass times acceleration is a force times a distance. So that's going to be newtons, actually. So this is roughly 1956 Newton meters, which is joules, actually. So it is a unit of energy. All right, so now let's pretend as though we flip the switch. That's how much energy is stored in that bullet that has been fired. Let's flip the switch and suppose that you personally weigh 70 kilograms. I'm just making this up, but 70 kilograms. And let's say you walk at 1 meter a second. So how much energy do you have stored in you as a mass when you move along? Well, you can easily see here when you do the mathematics, that's just going to be 1 divided by 2 times 70, or 35 joules. That's not actually very much. Now, if you take, for example, the kinetic energy of a jaguar that might be moving quickly, well, let's assume that jaguar has the same mass. This time, it's running at its maximum speed of 64 miles per hour, which is roughly 28.6 meters per second. Square that bad boy, divide by 2, and grab a calculator. Give me a moment. That's roughly 28,629 joules. That's a lot of energy stored in that mass, which is a jaguar. So you can see that's a very powerful, and we often think of bullets as being very powerful, but I could adjust these numbers slightly just to get these numbers to work out. That's maximum speed. Obviously, they can't maintain that burst forever. And so if I decided for that cat to go maybe 1/4 of its maximum speed. So it's going maybe 7 meters per second, which is a pretty fast move, honestly. If you do that, you get the following. Almost the same as the kinetic energy of that bullet that's being fired out of the rifle. And so that's equivalent to this cat or a human being, a 70 kilogram person, running at around 15 miles per hour. So that's pretty interesting. That's how much kinetic energy is in a bullet. So anyway, you didn't need to know all that for this problem, but I just thought that's kind of a cool side note. So anyhow, let's see. So if a force is acting on an object, making it change its velocity, let's say that you're increasing its velocity, you are adding energy to the system. And so there should be a net change in energy in the system. And that net change in energy is just going to be the difference between its ending energy, which I'll go ahead and show right here, and the beginning kinetic energy. And so what they want you to do is to let x be its position of an object at time t, and v and a be the velocity of the object and the acceleration of the object. And we want to prove this theorem right here, that the work done on the object, which is, as we know, a change in force, or basically a bunch of force times distances. Okay, so sum up all the forces times the distances. We want to showcase that that is equal to the integral from t1 to t2 of the force as a function of position times the velocity, and then dt. And that's actually pretty quick to prove. So let's go ahead and do that. So what we're going to do, I have to get a new pen out, is we're going to let x equal position. Now remember, we have the integral from position 1 to position 2. I think that's what they said. Yeah. Of f of x dx. Well, if x is a function of position, well then we know that dx is going to be the derivative of position with respect to time. So those are the changes we're going to make here. Going from x1 occurred at some time 1. So when x is x1, we are at time 1. And maybe I won't write that yet. Maybe I'll just go ahead and just say we're integrating the function, and x is s of t. And then dx is going to be traded out for an s prime of t dt. However, the derivative of position is the velocity. Now, something you should note here is that our variable of integration is time. So we're going to go from some initial time to some ending time. And I'm not actually going to solve that guy for time. I'm not going to say time 1 is s inverse of x sub 1 and time 2 is s inverse of x sub 2. I'm just going to say it goes from time 1 to time 2. Because it does. We don't know what those times are, but that doesn't matter. So anyhow, integral t1 to t2, f of s of t, and then v of t dt. And if I highlight that, I'm not going to highlight the whole thing, but and I scroll up here, you'll see that is actually what we wanted to get to here. And then they ask us to use Newton's second law of motion, that force is just mass times acceleration, and the substitution that u is equal to v of t to evaluate this integral. So I'm going to go ahead and, just for sake of our knowledge base, I'll say recall that force is equal to mass times acceleration due to gravity. And acceleration is just actually the second derivative of position, which is the first derivative of velocity. So what I'm going to do in this integral here is we're going to say let u be the velocity at time t. Then du is going to be v prime of t dt. And now we can go ahead and make our substitution. So let's see, the work done in moving the object from position 1 to position 2 is the same thing as we have just computed to be the work from time 1 to time 2 of the force at position times the velocity at time with respect to time. Now that work at the force at position there just means the force at a given time is really what that means. So using this substitution, everywhere that I see a v, specifically this v right here, I'm going to replace it with a u. Let me do that. Integral. I'm not going to trade in any limits yet. And then wherever I see a dt, well, actually, maybe I should trade this out. Maybe I'll say also, by the way, we know that force, let me highlight that guy. This force right here is mass times acceleration. Right? And again, that's at a time t. So force is mass of the object times the acceleration of the object, which is v prime of t. And remember, we're still in dt for the moment, but we know that dt times a v prime of t can be traded out for a du. So let me get completely into the world of u's. So this is mass times u du. And I'm not going to actually integrate this yet. We're actually still, I'll leave these as question marks and I'll worry about the transformation in a moment. So this is mass times u squared over 2. However, u is just v of t. So I'm going to say that's equal to mass times v of t being squared over 2. And velocity, when we are working with v of t, like this guy right here, we're going from time 1 to time 2. So time 1 to time 2. And that is going to be 1/2 mass times the velocity at time 2 squared minus 1/2 the mass of the velocity squared at time 1. And if you take a look at this guy, and I don't have enough highlighters left to really make a difference here. So if you just take a look at this statement, this difference between those two quantities, it is identical to this statement. Oops, you can't see it, sorry. To this statement right up here. It is the difference in kinetic energies. So we've actually just proven that work is actually the difference in kinetic energy from time 1 to time 2. So that's what part A was. It's actually kind of a neat problem. Now part B was now just using that. How much work in foot-pounds, so now we have to really worry about not being in kilograms and not being in the metric system. How much work in foot-pounds is required to hurl a 12-pound bowling ball at 20 miles per hour? All right, so I'm going to start kind of writing down the details of this problem, part B. We know the force is going to be 12 pounds. Remember, pounds is a force. And the velocity, at least at the end, is going to be, was it 12 or 20? I can't really remember. 20 miles per hour. 20 miles per hour. That's a problem. Miles per hour is a problem in the US system because when you're working in the US system, just like when you work in the metric system, in the metric system, you want everything in the kilograms, meters, and seconds. Well, in the US system, you want everything in pounds, feet, and seconds. And right now, this miles per hour is an issue. We have to convert it to feet per second. So let's see, that's 20 miles per hour But 1 mile is 5,280 feet. And, I should write the word feet in there. And 1 hour is 3,600 seconds. And I'm going to pause the video just to get a rough estimate here. All right. And so that is roughly 29.3. Actually, it's exactly 29.3 on forever feet per second. That's the velocity with which we are initially throwing this ball. Actually, initially there was no velocity. And at the end, we're changing its velocity to be 29.3 on forever feet per second. The other piece of this is that force is mass times acceleration. Well, mass in the US units is known as a slug. And to use our formula, which is this 1/2 mv squared minus 1/2 mv squared, to use that formula, we'll need to find the mass of this bowling ball, not the force or the weight of it, but the actual true mass, the mass that does not change whether you are sitting on Earth, the moon, Mars, whatever. Okay. So to do that, we have to know a constant, a gravitational constant on Earth, and that gravitational constant is roughly 32 feet per second squared. So I'm going to just put that in here. They actually give us that information in the problem. And so, reducing that down, see, they both are divisible by 4, so that's going to be 3/8. And so now I should probably, oh, by the way, the mass will be in slugs is the unit. If you didn't know what pounds second squared per feet is, it's slugs. That's the mass in the US. All right, so let's go ahead and use the formula. Now remember, the work done is supposed to be the change in kinetic energy from time ending to time starting, or vice versa, actually. Well, when we first start, so note, when you first start, the velocity at time 1 is 0. So there's really no need to worry about this second piece. All we need is the first piece. The mass is going to be 3/8. And the velocity is 29.3. Again, that's meters per second squared. I'm sorry, feet per second, and then squared. And that's approximately equal to, let me just pause this, 161.3, and this will be actually in foot-pounds. The reason why I know it's going to be in foot-pounds is that after we do all of our mathematics here, I know that it's going to be a work. But you can also kind of evaluate this using the fact that the units on this statement here are pounds per feet, per second squared, times, and then velocity squared, which is going to be feet per second quantity squared. Well, if you take a look at that, we'll have feet squared upstairs, so pounds times feet squared. Downstairs, you'll have feet time over second squared times second squared. So you can see those two cancel and everything else cancels to get foot-pounds in the end. So there you have it. That is problem number, 31 in 6.4. That's how much energy you have put into the system by throwing that 20-pound bowling ball.